In this video, I'm going to tell you all about the limit of the difference quotient and how that is going to help us find the slope of a curve at a single point, at a single x value. And where we're going to start this off is we're going to start it off with a secant line. So here in black, I've got this curve right here. It's a downward facing parabola, -1/2 x squared plus x plus 2. And I'm going to try and find the slope right at this point right here. Right, so it's an uphill slope. We look left to right. It's going uphill, and it looks like it's about a 45-degree angle, possibly a slope of 1, but I want to find it exactly. Now I'm going to start off by putting a secant line on here. So this secant line is finding the slope between, or the slope of this line is going to give us the slope between 2 points on our curve. And I can move it back and forth I'm using Desmos.com. In fact, I'm using, if you Google limit definition of the derivative and Desmos, it should come right up with this. The URL is desmos.com/calculator/JURNQTCLTF, and you should be able to use this same demo right here. So the idea is that I'm going to take my secant line, and I can think of my secant line as an approximation of the slope right at this point, the slope of the tangent line right at this point. And the closer my two x values, my 2 points are together, so this point and this point, the closer these 2 points are, the better an estimation it is. This estimation is way off, hardly even call it an estimation, since this is a negative slope and my tangent line is clearly going to have some kind of positive slope. But the smaller I make the distance between the 2 points, the better my approximation is going to be. And this variable h is set up so that it gives me the distance between those two x values. And of course I can slide it all around here. H is always going to be the letter that we're going to use for this. Although some teachers will use delta x, especially if you're in maybe a physics course, so the change in x. Right, so if you move it right there, we get the exact point we want. So this right here at the top of the screen is the limit of the difference quotient. We have a limit as h approaches 0. This is the exact same h that we had before. This h represents the distance between two x values. We want that distance to approach 0, where those two x values are infinitesimally close to each other. And then this right here is the difference quotient. It's a very silly name. It's named because there's a difference, a subtraction, and a quotient, a division. And that's it. And a very important thing to remember is that the difference quotient, all by itself, is the exact same thing as the slope formula. H is the distance between two x values, the same as if you had x2 minus x1. And then up here, this is like plugging in x2 to our function to give us our y value, y2, minus our y value of y1. So this is rise over run. This is y2 minus y1 over x2 minus x1. But we want our x2 and our x1 to get really close together. Now, if we just said that x2 equals x1, then, and we subtracted them in the denominator, we'd have a divide by 0. So we have to use the limit to get around that. This is the function that we were just looking at down at the bottom of the screen here in Desmos. And we're going to use this formula to find the exact slope at the same x value we were looking at before at the x value of 1. So let's see what we can do. So there's our x value of 1. A really useful thing is to think about our original function with a big gap wherever there was an x. We're going to do a lot of substituting into this function. So it's useful to look at your function in this way. The first thing that we're going to substitute in is we're going to plug in 1. 1 is our x value that we're interested in. So instead of x, each time there was an x, I put in the value of 1. And then I just cleaned it up a little bit, right? So -1/2 times 1, that's just -1/2. 2 times 1, that's just 2. And then 2 plus 2 is 4, plus a -1/2 is going to give us 3.5. So we're going to use this a whole bunch, because if we go back up, we have our f of x right here in our formula. And our x is 1, so we're going to be subtracting f of 1. So it's nice to have that calculated. The next thing that we're going to do is we're going to plug in f of 1 plus h. That's the other part of the difference quotient that we need. So here is what it looks like when I plug it in. I'm not going to square this yet. I'm not going to distribute this 2 in, but I will do that shortly. So Here's our limit of the difference quotient. I say ours because we're going to use the x value of 1. We want a specific slope value at the x value of 1. And now we're going to start substituting in the different pieces of this. For example, f of 1 plus h, well, what does that equal? It equals this whole thing right here. So we're going to substitute that whole piece into this location. So there we go. That's what we've done right here. You see that whole f of 1 plus h, all of that is this part right here, all the way to the plus 2. And then minus f of 1, which is right here, the 3.5. And we're subtracting these things. It's a difference, and then the quotient part is the division part. All right, now we need to start cleaning things up. So I'm going to square the 1 plus h. That means I need to FOIL it. I'm going to get 3 terms right here. I'm going to distribute the 2 in, so now I have a 2 plus h instead of a 1 plus h. Okay, so I've got my plus 2 here, and a minus 3.5. Well, that's 4 minus 3.5 is just going to give us 1/2. That's kind of nice. And the very next thing I'm going to do is distribute the negative 1/2 in. All right, so from this step at the top to this step at the bottom, I distributed the negative 1/2 in. That's all I did. Hopefully you see what's going to happen next. We've got a negative 1/2 up top and a 1/2 over here on the right side. Those are going to cancel. Stuff should cancel as you're going through the process of evaluating a limit of the difference quotient. If things don't cancel, probably some kind of mistake has been made, because our ultimate goal here is to get h out of the denominator. We can't plug in 0 for h when there's an h in the denominator like this that's going to cause a divide by 0. So to get to this step right here, all I did was cancel the positive 1/2 and the negative 1/2. You'll notice that all these terms have an h in them. The first thing I'm going to do, though, is I have a negative h and a positive 2h. I can combine those into just an h. They're like terms. And then the next thing I'm going to do is I'm going to factor an h out of the numerator. I'm going to factor an h out because if I can take an h out of each term in the numerator, that means that I can cancel these h's, which is the very next thing I'm going to do. All right, so here's my h's. I'm going to cancel them. This is what's left over. There's not even a denominator. So this means it is very safe for me to plug in 0 for h, and that's what I'm going to do, and you'll probably see what I'm going to be left with. So I plug in 0 for h. Negative 1/2 times 0 is 0. I get 1. Let's check back in on Desmos and see if this looks like this is the slope that I should be using. So here's my graph again on Desmos. Here's my tangent line. This line has a slope of 1. You can see it with the rise over run, right? Here's a y-intercept at, looks like 2.25. But if I go up one of these boxes and write 1, I hit the line again, up 1 over 1, up 1 over 1, up 1 over 1. I have a slope of 1. So the limit of the difference quotient has given me the precise value of the slope at a particular point on a curve, right? A curve has many slopes. The slope changes as we move across the x-axis. And now we have a way to find the slope at a particular point. Let's do another example. So I just took my previous Desmos example and I modified it for a new function. So my new function is 2 times square root of x plus 4, the line in black right here. And I've got a secant line drawn again in red. And here's my h value. And I'm going to adjust my h value. So we can see here that this is not a very good estimate of the slope right at the x value of 5. By the way, x value of 5, that's what we're gonna try and find the slope of the tangent line right there. And by the way, I'm choosing these numbers arbitrarily, right? 5 is just, I decided on that for the value that I want. I mean, I decided on it because 5 plus 4 is gonna be an easy square root, just to make it a little bit easier on us. So if I take my distance between my x values on my secant line here, and I begin moving them back, we see how this red line, its slope changes, and we get a better and better estimate for the slope right at the point of 5. Now you'll notice the line actually disappears when I'm right at that point. That's because I'm going to have a divide by 0. I'm going to be dividing by this h value, or the distance between my x values, and that's 0. So Desmos is not going to show that line. So I can get really, really close, but I can't just put the line there. Not unless I have some help from some calculus. Here again is the limit of the difference quotient up top. And then the function that we're particularly interested in, 2 times root x plus 4. We're interested in the x value of 5. That's where we want to find what the slope is. And again, I recommend writing down the function with a big old set of parentheses with a lot of space wherever there was an x, because we're going to be substituting some stuff in here, and we want to make sure we do this correctly. The first thing that we're going to substitute in is the x value of 5. So I plug in 5. right where my other x was. 5 plus 4 is 9. Again, I chose this because the numbers are going to be easier. Square root of 9 is 3. 2 times 3 is 6. So our y value at the x value of 5 is 6. When I go ahead and plug in 5 plus h, again, right where the x value was, I'm going to plug in my 5 plus h. These parentheses are not strictly necessary. I just want to emphasize where the x was located. And then the 5 and the 4 right here, they can actually combine. We can drop these parentheses. 5 plus 4 is 9. And then this is what 5 plus h equals. Okay, so I'm going to use this and what I had for f of 5. I'm going to substitute into the limit of my difference quotient. So here is the limit of the difference quotient with 5 plugged in for x. We just calculated this y value, this f of x, the f of 5 plus h, and the f of 5 over here. So that is 2 square root h plus 9 on the left minus just 6 on the right. If we try and evaluate this limit, well, if we try and plug in 0 for h, we got to divide by 0, as we're always going to have with the limit of the difference quotient. So we need to figure this out. We're going to use the conjugate trick. We're going to multiply by the conjugate of this numerator in the form of 1. So that's what I have right here. So I take my numerator, and it's not necessarily the numerator. It's just the part that's going to have the square root on it. In this case, it's the numerator. So I'm going to take the conjugate of this numerator, which means instead of a minus between my two terms, I'm going to change it to a plus. If it was a plus here, I would change it to a minus. And I need this to be a 1, right? The rules of mathematics say we can multiply by 1. I can't just multiply by something arbitrary because that would change what my question is. That would change what I'm actually evaluating here, what the expression is. So I want to multiply by just 1. That's always allowed, doesn't change anything. So I put that numerator over itself. All right, and then when I go ahead and multiply across, in the denominator, I'm not going to distribute this h in. I don't want to do that. My ultimate goal is to cancel this h out because the h is causing a divide by 0. So we're just going to leave the h factored out on the outside, put a set of parentheses, and that's all fine and good. The numerator, however, I want to foil this, right? First, outer, inner, last. I want to multiply these all together. And I claim that I get this. That's simplified a lot. So let's talk about what happened. So first, I multiply 2 square root h plus 9 times 2 square root h plus 9. Well, 2 times 2 is 4. Square root h plus 9 times square root h plus 9 is like I squared it, which is the inverse of the square root, so the square root goes away. So I end up with 4 times h plus 9. Make sure to leave these parentheses here. It's tempting to just drop them, but this 4 has to distribute into both the h and the 9. Both the h and the 9, they deserve a 4. Don't leave the 9 out, right? Everybody deserves a 4. Make sure you remember to distribute that in by leaving these parentheses here. And then outer and inner of the FOIL, right? So 2 square root this stuff times 6 minus 2 square root this stuff times 6, or 2 square root this stuff times negative 6. Well, when you add those together, they're going to cancel to 0. And this is the magic of conjugates. This is why we chose conjugates, because they're going to cancel out nicely in this way. And then finally, last, negative 6 times positive 6 gives us negative 36. And you probably see what's going to happen next. If you distribute this 4 in, which I do right here, 4h plus 36, we have this convenient canceling just set up for us. So 36 minus 36 is 0. And now these h's can cancel as well. And again, like I said before, if things are not canceling as you're going through this process, probably something went wrong. I would look for an arithmetic or an algebraic mistake. These h's cancel. Now we have the following. Now we can plug in 0 for h, so I do so right here. Notice I'm no longer writing limit as h approaches 0 as soon as I've plugged in. That's where the limit has done its job. As soon as we're able to plug in whatever h approaches, then I'm no longer evaluating this limit anymore. Now I just have this expression right here that I'm going to figure out what its value is. So square root of 0 plus 9 is just square root of 9 is just 3. And now we can sail on through to the end. 2 times 3 is 6, plus 6 is 12. 4 over 12 is 1/3. Let's jump back to Desmos and see if this gels with what we expect our tangent to be. So I'll take off the secant line, put on the tangent line right there. And let's see here. All right, so this looks like it could be a slope of 1/3. Now I could actually look at the line equation, but I'm not gonna worry about that. Sure looks like I cross at this point. Let's go up 1 and write 3 of these blocks. And I get to this point right here. Let's go up 1, right 1, 2, 3. Looks like I'm still on the line. Up 1, right 3. I'm still on the line. Sure looks like a slope of 1/3 to me. So the limit of the difference quotient right here is giving us the exact value of the slope of some function at a particular x value.